Hi, my name's Rebecca Monahan, and my topic is on paleosols. So, paleosols are ancient soils that are formed by burial and are a powerful tool for reconstructing ancient environments. So, paleosols now constitute a smaller proportion of continental crust rather than most other well-known rock types. The proportion of paleosols appears to be particularly small in the oldest rots. In these rots, the preserved portion is so small, and the conditions for preservation of paleosols appear to have been so peculiar that it is dangerous to make sweeping interpretations of ancient Earth environments based on paleosols. But my thesis is paleosols are excellent recorders of ancient environments because they help form the key to ancient environments and show features from the past. So, paleosols and sedimentary rock. So, paleosols are known from all major divisions of Earth's history, from the Archean eon to the present epoch. The proportion of paleosols to other rock types greatly increases with time, consistent with the theory of continental growth through Earth history. An increase in the area of exposed continents would lead to an increase in the volume of soil. Additionally, tropical climates can increase the growth of distinct soil and paleosols. So, due to wet conditions, soils can be produced that are rich in aluminum, causing the leaching away of groundwater and vegetation decay. As a result, this decay produces acids that attack even quartz, leaving only aluminum rich minerals. Aluminum rich paleosols are among the oldest Archean paleosols on Earth, so wet tropical conditions appear to have existed long ago. So, elemental composition and mineralogy. So, interpretation of the elemental composition and mineralogy of a paleosol is dangerous. Precambrian paleosols, which are older than 544 million years, contain extreme comparisons of potassium to sodium, unlike modern clayey soils. This is found interesting because no weathering process could produce this extreme ratio. So the potassium in Precambrian paleosols either is a record of pervasive diagenetic alteration of Precambrian paleosols or indicates that, unlike modern soils, they did not form as a result of atmospheric acid-forming gases. So the majority of Precambrian paleosols could identify changes on the ancient land resulting from exhalation of acid-containing mud from deep in the earth. So basically it's saying that these paleosols contain extreme comparisons of potassium to sodium, and they did not form as a result of atmospheric acid-forming gases, and the majority of them could identify changes on the ancient land. So just a little bit, again, of background of paleosols. So when soils buried or at the modern surface are considered to be older than the soil that is developing at the present time, they can be classified as paleosols. So there are three types of paleosols. Rhyolite soils, which have remained on the current land surface since the time of initial formation, but do not necessarily reflect the processes forming today's soil. Buried soils, which formed on ancient land surfaces that were subsequently buried by a younger deposit, and exhumed soils, which were initially buried but were later exposed by erosion. So all these soils are beneficial in investigating climate change, but buried soils have been the most important in deriving climate information for a great number of quaternary time intervals because they have remained protected from most alterations since their formation. So again, paleosols are found worldwide under a range of conditions. However, places where widespread studies have occurred stand out. So for example, paleosols formed in glacial deposits have been important in identifying glacial climates and in identifying ancient surfaces. What makes glaciated regions unique is that distinct climates are commonly associated with specific material types, such as cold climates with till and warm climates with superimposed soils. Interbedded paleosols are also frequently discovered in Holocene sand dunes all through the world. So these paleosols are usually poorly formed because they were commonly covered by sand before they had time to fully develop. So paleosols are found under a range of conditions, but some examples of them are found in glacial deposits, and also they're frequently discovered in sand dunes. So estimating the ages of paleosols, the length of time that a surface has endured weathering can often be assumed, although there may be some doubts. So estimating the length of time it took for any soil to develop, i.e. before it ceased to actively form because of burial, is difficult to calculate, in part because the soil typically forms over thousands of years. So as a result, this creates a dilemma in identifying paleosols and the time in which they were formed. A method to help assist in estimating the age of paleosols is radiocarbon dating. So radiocarbon dating of inorganic carbon, mostly secondary calcium carbonate, is another method of establishing the age of a paleosol. Datable secondary inorganic carbonate can be deposited on soil particles or even on the base of pebbles below the main soil horizons. The inner older layers of carbonate in these deposits are protected by younger layers, offering the best opportunity for determining maximum age. Secondary carbonate in the lower part of a sea horizon, where solutions may no longer be active, also offer opportunities for finding the oldest age. So, another method to estimate the age of the paleosol is to date the material that overlies and underlies the paleosol. For example, if the material overlying the paleosol near the soil contact is 10,000 years old, and the underlying material near the lower contact is 15,000 years old, then the soil took about 5,000 years to develop. So, for estimating the age of paleosols, the best forms or methods of doing that is radiocarbon dating and dating the material that overlies or underlies the paleosol. So, an example where paleosols can be found is in the Chinese Loess Plateau. So, the Chinese Loess Plateau provides the lengthiest known unbroken quaternary paleosol record and offers a large amount of information on climate change and the forcing mechanisms involved. Complete A horizons are common, but many have been partially or totally eroded, and in some cases part or all of the B horizon is missing. By noting the presence or absence of glaciation, which is the process involving the reduction of iron in saturated soils, commonly indicated by black FeMN films and modelings, and the concentration and character of clay coatings, it is possible to recognize 4 types of B horizons. So these include a weak BT or BW, a moderate BT, a strong BT, and a very strong BT. So the specific type that is present reflects the intensity of weathering, allowing the climate and vegetation under which they form to be interpreted. The strongest BT horizons suggest the presence of a relatively dense forest or steppe forest vegetation and a relatively stable landscape with a pronounced seasonal wet-dry alternation during soil development. So the Chinese Loess Plateau can provide quaternary paleosol records, and B horizons are the most common, where you can find ancient climate and examine it. And the strongest, again, BT horizons suggest the presence of a relatively dense forest or steppe forest vegetation in a relatively stable landscape. So in contrast to that, at the other end of the spectrum, a weak BT horizon in the buried soil represents steppe forest vegetation, a relatively stable landscape, and wet-dry alternation, but with generally less precipitation than that required for a strong BT horizon. So the development of Chinese paleosols occurred during a climatic regimen like that prevailing in the Loess Plateau today, where weathering occurs within the context of the humid summer monsoon and the dry, cold winter monsoon. So in contrast to that, a weak BT horizon represents a steppe forest vegetation, but it generally has less precipitation than that required for a strong BT horizon. And I just put in here a couple few points to remember. Paleosols are a valuable tool in examining quaternary events and understanding past environmental conditions. And identifying and locating a specific B horizon is particularly important in helping to determine former climates. And information on past climates can generally be derived from paleosols and may include proxies for both climate and vegetative cover during weathering. Additionally, determining the actual interval of time during which a paleosol formed is difficult. Although various methods can be employed, probably the most accurate in the case of buried soils is obtaining bracketing ages from datable material above and below the paleosol. So paleosols are a valuable tool in examining quaternary events, but determining the actual interval of time during which they formed is difficult. So the most helpful tool is obtaining bracketed ages from datable material above and below the paleosol. And another area where paleosols exist is the Caringrad Loess Paleosol section in, I think it's eastern Croatia. So eastern Croatia is mostly covered by quaternary deposits, which were deposited on Mesozoic, Miocene, and Pliocene sediments, as well as magmatic and metamorphic rocks. Since the end of the Miocene, the slow uplift continues in the central part of the Fruška Gora. Subsidence of its northern and southern slopes has resulted in increased sedimentation during the Pliocene and Quaternary periods. The base of the investigated Caringrad section consists of about 1 meter of yellow to light brown miocasous fine-grained sand and weakly sedimented sand of fluvial origin. The clays represent marshy sediments and are overlain by a grayish variegated clay with red and brown stripes and patches caused by enrichment in dispersed limonite and manganese precipitates. So the paleosols present consist of a transitional horizon on the top, an AB horizon in the middle, and a thin C horizon at the bottom. The AB horizon is composed of red-brown silty clay and becomes darker with depth. So the fossil soil level is strongly compacted, homogeneous, and unstratified. Below the AB horizon, a 0.2 meter thick horizon of carbonate accumulation and sedimentation has been recorded. This paleosol is a Chernozem brown forest-type soil and is covered by a Loess horizon about 7 meters thick. Above this thick Loess horizon is a double fossil soil containing 2 paleosol subhorizons. It is overlain by a Loess layer seen at the uppermost inaccessible part of the section. So my presentation was about how paleosols are helpful in identifying ancient climates because they help form the key to ancient environments and show features from the past. Okay, thank you.